At an ocean trench, seawater seems to meet solid earth and disappear. The vanishing is not a drain, but a journey through fractured rock. An oceanic plate bends downward and carries hydrated minerals beneath another plate. Some water occupies cracks, while some becomes bound inside mineral structures. The central mystery is how far that water travels before returning. From the surface, the trench appears only as a long, dark valley. Below it, chemical cargo descends through temperatures and pressures that transform rock. Each transformation can release water, trap it again, or drive melting. The pathway controls volcanoes, earthquakes, and Earth's long-term water exchange. Yet, scientists cannot watch a water molecule complete the entire underground route. They reconstruct the journey from rocks, seismic waves, experiments, and volcanic chemistry. These lines of evidence overlap, but none alone closes the global budget. You followed the plate. Familiar liquid water would soon become uncommon. Water persists mainly inside pores, faults, and hydrous minerals during descent. The trench is therefore an entrance to a changing geological transport system. Oceanic crust forms at mid-ocean ridges and cools while moving away. Seawater circulates through fractures, altering basalt and underlying mantle rock. These reactions incorporate hydrogen and hydroxyl into newly formed minerals. Sediments settling on the plate also contain pore water and hydrated minerals. By the time the plate reaches a trench, its water has several hosts. The plate bends sharply near the trench's outer rise before subduction. Bending opens normal faults that can penetrate deep into the oceanic lithosphere. Seawater may enter those faults and react with exposed mantle peridotite. Hydration of peridotite can produce serpentine group minerals through serpentinization. Serpentinization changes rock density, strength, chemistry, and seismic wave speed. Reduced wave speeds can indicate hydration, although temperature and structure also matter. Seismic imaging, therefore, constrains possible hydrated zones rather than photographing water directly. Rock samples from exposed fault scarps provide direct evidence at accessible surfaces. Laboratory analyses identify hydrous minerals and estimate their stored water content. Such samples may not represent deeper portions of the faulted plate. Sediment thickness also varies among trenches, changing the incoming water inventory. Warm young plates and cold old plates follow different thermal paths. Temperature matters because hydrous minerals remain stable only within particular conditions. As the slab descends, pressure increases and mineral structures reorganize. Some reactions release water into the overlying mantle wedge. Released fluids lower the melting temperature of mantle rocks nearby. Partial melts can rise, feed magma reservoirs, and ultimately support volcanic arcs. This verified sequence links trench intake with volcanism far inland. Faults can channel fluids locally and influence where reactions proceed fastest. Dehydration reactions may also alter stress and promote certain intermediate depth earthquakes. This connection is a mainstream interpretation, not a universal explanation for every event. Earthquake waves reveal slab geometry down to hundreds of kilometers. They cannot directly measure the water content of each descending mineral grain. Electrical conductivity can rise where fluids or melts connect through rock. High conductivity remains ambiguous because temperature, composition, and melt fraction also contribute. Volcanic gases contain water released from magma approaching the surface. Their isotopic and chemical signatures help trace mixed mantle and slab contributions. However, eruptions sample processed outputs rather than the original trench inventory. You might imagine subtracting volcanic water from incoming seawater to balance everything. In practice, uncertain volumes, hidden storage, and recycling make that arithmetic difficult. Some slab water returns through arc volcanoes, springs, and diffuse degassing. Some may remain locked in minerals descending beyond the main arc. Dense hydrous magnesium silicates could carry water into the deeper mantle. Their importance depends on slab temperature, composition, and reaction completeness. Cold slabs are generally capable of transporting certain hydrous phases deeper. Warm slabs tend to release much of their bound water at shallower levels. Even cold slabs contain fractures and chemical variations that complicate simple models. Mineral inclusions in diamonds provide evidence that water-bearing components reach great depth. Those inclusions demonstrate deep storage, but not the precise route or global amount. High-pressure experiments test which minerals remain stable along plausible slab conditions. Experiments simplify natural rocks and operate over much shorter timescales. Thermodynamic models extend results across temperatures, pressures, and bulk compositions. Their predictions depend on accurate mineral properties and realistic starting materials. The strongest conclusions emerge where field observations and experiments agree. This hidden circulation shapes habitats around volcanic arcs and forearc springs. Fluids rising from slabs carry dissolved elements into crust and ocean. Microbes can exploit chemical disequilibria where those fluids reach cooler environments. At some forearc sites, serpentinization supports alkaline, hydrogen-rich fluids. Microorganisms use available chemical energy, alter compounds, and influence local ecosystems. Their activity records a biological consequence of water-rock reactions below. Arc volcanoes create islands, mountains, soils, hazards, and atmospheric emissions. Magma generated with slab-derived components can erupt explosively when gases expand. That Q-action consequence chain begins with buried water and ends near human settlements. Subduction-zone water also affects rock strength and patterns of seismic deformation. Elevated pore pressure can reduce effective friction along particular fault regions. Yet fluid pressure is difficult to observe directly at earthquake-generating depths. You should therefore treat correlations between fluids and earthquakes as constrained interpretations. The global cycle operates over millions of years and across many contrasting margins. It links ocean chemistry, mantle composition, crustal growth, and volcanic degassing. Whether Earth's deep interior gains or loses water remains quantitatively uncertain. Estimates of subducted flux differ because hydration depth is poorly known. Return flux estimates differ because volcanic and diffuse emissions vary through time. Better budgets require comparable measurements across representative subduction zones. Human drilling can sample only the shallowest part of incoming and overriding plates. Future seismic arrays can resolve finer changes within bending faults and slabs. Seafloor electromagnetic surveys can test whether conductive pathways align with fractures. Improved ocean drilling could measure hydration before the plate enters a trench. Pressure experiments should reproduce more realistic rock mixtures and reaction pathways. Volcanic monitoring can compare water output with magma supply over complete eruptive cycles. Integrated models must track uncertainty rather than forcing one exact global number. If you return to the trench, the apparent drain now has structure. Water enters pores, faults, sediments, and mineral lattices on a bending plate. Part escapes beneath forearcs, while another fraction reaches arc-generating depths. Some bound water may continue far deeper than volcanoes reveal. Testing that possibility requires mineral evidence linked to credible pressure histories. No sonar image can show the complete route beneath the seafloor. No volcanic sample can represent every molecule carried down by the slab. The next decisive evidence will constrain deep hydration before and during subduction. Until those measurements converge, the balance between return and deep storage remains open. Ocean trenches carry water inward through sinking, reacting rock, but its ultimate destination is still incompletely measured.